Our next talk will be given by Jihyeok. He is a professor at Korea University in Seoul. His work sits at the frontier of formal methods and real-world language design. Jihyeok is known for his research on executable semantics of JavaScript. It's a work that bridges theory and tooling in a way that is both rigorous and practical. Today, Jihyeok will share insights from building ESMeta, which is a tool chain that automatically extracts a mechanized JavaScript specification from the prose of the JavaScript specification document. So let's welcome.
Okay, thanks for really nice introduction. So hello everyone, I'm Jihyeok from Korea University. So in this talk, I'll explain how to support trusted JavaScript language environment with our tool chain called ESMeta. So let's start from the basic the background. So JavaScript has official language specification called ECMA 262, and it is maintained by the ECMA Technical Committee 39, shortly TC39. So it is kind of book, contains more than 800 pages, and it describes the JavaScript language syntax, looks like this, and describe the semantics using the algorithmic English prose. So each algorithm contains different step-by-step execution, how to evaluate different syntax or between libraries. So for example, it describes the syntax of addition, and this is the semantics for addition operator, but it only has a single line of the step, but it refers to another algorithm. So we need to understand at least more than 100 steps to understand the full edge cases of the semantics for addition, because JavaScript is the dynamically typed language, so it supports addition between different types of values. And in the real world, there are a lot of different language tools for JavaScript, including JavaScript engines, usually in web browsers or Node.js, and transpilers and other research tools. And all these tools should conform to the semantics describing the specification. And if a new language feature is introduced, then all these tools should update. They strictly conform to the updated semantics in the specification. And the tool developers should check the conformance between their tools and the specification. But the problem is that all this process is manual. It means that we need to update the specification and also tools, and checking the conformance is all manual process. It is labor intensive and tedious and even error prone. But actually, this problem is not a big problem until 2015, because JavaScript has been rarely updated. But since 2015, the problem becomes a more critical problem, because TC39 decided to update the language specification for every year to support the new language features for developers. So yeah, this is a real problem it becomes. And so to resolve this problem, we think that if we have a mechanized or executable formal specification, then we believe that we can resolve this problem. So we want to extract executable and formal specification, just to be shortly called mechanized specification, from the language specification written in English prose. Then we, using this mechanized specification, we want to automate all this process and even do more things using this extract and mechanized specification. So in this talk, I will introduce multiple things. First, how to extract the mechanized specification, and then using this extract and mechanized specification, what we can do it. So let's start from the first part, how to extract the mechanized executable formal specification from the language specification written in English prose. So again, I said that the specification describes the syntax and semantics, looks like this. So this is the syntax and semantics for the array literal syntax features. So as you look at this one, so there are multiple steps in the description of the semantics for array literal, but you can find several patterns, because it is the algorithms, not just any general English prose, it is algorithms. So we can define local variables using let, blah, 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 and we can invoke another algorithm using this syntax, and we can invoke other syntax-directed operation for abstract syntax trees, ASTs, shortly SDO for ASTs, using this syntax. So we found that there are some common patterns. If we define these common patterns as a meta-language, then we can mechanize or convert this English prose into some meta-language programs. So we define our meta-language just for specification. You can think of this meta-language as specification language or DSL or meta-language to describe the specification for JavaScript. So we call this meta-language as IRES, intermediate representation for ECMAScript specification, shortly IRES. So the most distinguished part compared to the general programming language is this one, because we need to treat JavaScript abstract syntax tree, for example, JavaScript expressions or statements as also values in this program. So we can pass JavaScript ASTs to another algorithm, so we can return some ASTs and so on. So we first designed this meta language to capture all the common patterns in the description in the algorithms. And then we developed this tool. So this tool, this was our first tool. It takes the language specification, and then there are two different parts. Based on the syntax part, we automatically generate parsers based on the parsing expression grammar techniques, PPAC. And also the core part is this one. We design a compiler. It takes the abstract algorithms and it produces our meta language functions. Looks like that. So the result is generated parser and the set of our meta language functions. So we call this one as mechanized specification. Now if we have the interpreter for our meta language, we get interpreter for JavaScript. So for any given language specification for JavaScript, we can automatically extract interpreter for JavaScript. So we often called it is the definition or interpreter for JavaScript. So the core part is here. We carefully manually design the compilers to compile each algorithm step to the corresponding our meta language instruction. For example, here, our compiler takes this the first step and produces this single meta language instruction. Our IRES instruction looks like this. So at the first time, we manually designed 118 compilers, but now we have slightly more compilers to cover more different common patterns in the language specification. So this is how to convert the official language specification into executable form or specification written in our meta language. Now, after extracting this mechanized specification, we want to automatically check the availability or found some bugs in the specification. To detect some bugs in the specification, we design a type analysis on the specification. So I'll explain how to perform type analysis on the specification and why it is useful to detect the specification bugs. So here is another algorithm that describes the semantics of the built-in library method run. So I will show you what happens if we perform the type analysis on this algorithm. So first, the parameter X can take any JavaScript values or sometimes ECMAScript values. So it can be string, Boolean, number, object, and so on. And after invoking this algorithm to number, it returns some JavaScript number values or exception values. So JavaScript exceptions are also values in our meta language. So it sometimes returns number values or sometimes exception values, JavaScript exceptions as values. But here we have this question mark operator. It is kind of filtering operator. So it filters exceptions. If the return value of the number is exception, that it just stops executing the remaining part and just go back, returns that exception values. So after this filtering operator, we only have number values. So the local variable n now only have the number value. But actually, this is the wrong specification. And this is not official language specification. Actually, the ECMA 262 is maintained as an open source in a GitHub repository. So I found this spec in the internal version of the ECMA 262. So here, in steps 3 and 4, the variable x are used instead of n. It means that this algorithm tries to compare the non-numeric values. For example, if we pass Boolean values to the x, then true or false will be passed to the x. And this algorithm tries to compare the Boolean values with mathematical values. But in the specification, there is no meaning. So it means that there is no semantics for that case. So this is obvious specification bugs. And before releasing the official specification, now it is fixed to look like this using the n, the variable n instead of x. So now we have the semantics for when we pass the Boolean values to this platoon library. So if we perform type analysis, we can automatically check these problems. So we built a tool called JSTAR, the set type analysis tools on the specification. Using this tool, we detected 93 errors in the specification with the 59.2% of analysis precision. And among them, 14 are newly detected bugs by our tool. And also, now this tool is officially integrated into the CI system in the ECMA 262. It means that any commit or pull requests are introduced in the repository. Our tool automatically try to perform type analysis on the updated spec, and we can give some alarms to that detected with the detected specification bugs. But actually, the problem, it is not enough because the precision is quite not that high. So it means that we have a lot of false alarms. So for example, here is an example of false alarm. Here, this is another algorithm that describes the semantics related to regular expression. So here, the parameter pattern can have any ECMAScript value, but here, the algorithm get requires object type as the first for the first argument. But this algorithm tries to pass the pattern as the first argument of the get. So it looks like a specification bug, but actually it is not. It is the false alarm, because to reduce this false alarm, we need to understand the more type information or type constraints in this algorithm. For example, here, isReg_exp always return normal Boolean type. Normal Boolean means that some completion, some specific kind of record type, and whose value field is Boolean type. So normal completion record and whose value field is Boolean. But here we need this additional type information, the implication between the return value and the parameter types. So here, if the isReg_exp algorithm returns normal true type, then always the parameter type is object. So we need to infer this more type constraint when we analyze the isReg_exp. So let's assume that we can do it. Then we can propagate this information into another part that looks like this. After applying this filtering operation, we get this information. Now pattern isReg_exp variable is Boolean type, but we have more information. If pattern isReg_exp is true, then we know that pattern is always object, even though at this point pattern can be any ECMAScript values. So using this information, we can apply this inferred type constraint here and here, because we know that now in this branch, we know that pattern isReg_exp is true, always true. So after applying this inferred type constraint, we can safely, soundly refine the type of the pattern variable into the object type, so we can safely remove these two false alarms. So this is the ongoing work. So actually in submission, so we try to increase the precision using this kind of advanced type analysis techniques. So the first application is to detect some bugs in the specification. The second application, we want to check the complements between the real-world implementation, the language tools, and the specification. So yeah, let's start. So I said that all the language tools should conform to the semantics describing the specification. And how to check the complements? The common way to check the complements is to utilize the conformance test. So a single complement test is just JavaScript program consists of two different parts. A JavaScript program that we want to check the complements and the assertions that describes the behaviors of the program. For example, it is kind of complements test. So this JavaScript program should throw a type error. And there exists an official test suite called test62. But again, the problem is that it is maintained by manual. It means that we cannot know that it strictly conform to the semantics described in the specification. And also we do not know that how many parts in the specification is covered by this test suite. So to resolve this problem, we want to automatically synthesize this complements test from our mechanized specification. To do that, we developed this tool. The core idea is just mutation-based buzzing based on the specification coverage. So this tool takes extract the mechanized specification and then first synthesize really simple basic program based on the syntax to cover all different syntax, and then iteratively mutates the program looks like this to cover more parts in the specification. So it means that we utilize specification coverage to guide the mutation. And finally, after converting the specification coverage, we automatically inject assertions based on their final stage. How to do that? Because this mechanized specification is the JavaScript interpreter. It means that we can execute all this synthesized program on our mechanized specification. We can get the expected final states according to the specification for the specific semantics in the specification. So using that, for the final stage, we can safely correct assertions for each program looks like this. So I said that we utilize specification coverage. It means that if we have this program, we can cover this one, we can cover this one, we can cover this one with these programs. But actually, this specification coverage, we think that that's not enough. Why? Because some algorithms shared by different language features. For example, this algorithm is used in different language features, for example, addition, subtraction, and multiplication, and so on. It means that even though we cover this edge case based on using this program, but we only covers this edge case in the addition. We want to cover all the edge cases in the semantics for different language features. So we propose slightly more coverage metrics, different coverage metrics called feature-sensitive coverage on the language specification. So based on these new coverage metrics, we need to cover all different specification part split by the related language features. So based on this one, we can cover more different semantics edge cases during the synthesis process. So based on these techniques, we detected 42 bugs in real-world JavaScript engines and 94 real-world bugs in the trace pilers. So we generated complements tests directly from the language specification. And after that, we realized that, oh, this complements test or the synthesized simple program is really good to understand that edge cases. It means that if we show the programs for each specification part, then we can enhance the understanding of the readers of the specification. So we develop a visualizer, looks like this. There are two different parts. We, using the previous part, we minimize the program and then filter the conformance test for different language specification part. And we showed the different programs related to that specification part. And also we support interactive double debugger. We can interactively execute the given program at that point. So I will give you with this demo. So actually this first part, so this is the official language specification, and you can install our visualizer as a Chrome extension. After clicking this one, you can see these three right side panel. And for example, let's go to this algorithm. And if you click looks like this. Okay, this program 1+1 is related to this part. If you click this one, then this program or this conformance tests are related to this part. It means that you can test this edge cases based on the test physics 2 conformance tests. For example, let's click here and you can say this program. Now you want to interactively execute that small JavaScript program. You can click on run on double debugger at this point in here. Then you can see this double debugger, interactive debugger. Now, if you click resume button, then it directly goes to the specification part you want to understand. And then you can interactively backward or forward, looks like that. And the right part shows what happens in the specification and also what happens in the JavaScript. So you can see both different states related to the specification and the JavaScript. So we call it as double debugger. So the last part is about the derivation of the language tool. So far we only checking the complements and the detect the bugs in the specification, but we want to derive the language tools directly from the mechanized specification. So there are a lot of different language tools, but our first target was the static analyzer. So we want to derive the JavaScript static analyzer from the mechanized spec. So it means that we have this specific version of spec, and we want to analyze this program. Using our extraction tool, we can extract this mechanized spec. I said that this is JavaScript interpreter written in our metalanguage. If we have static analyzer for our metalanguage, then we can analyze this interpreter. So it means that this analysis research has possible behaviors of an interpreter. But if we restrict the initial state based on our target program, it means that we want to analyze this interpreter, but only when it takes this program. So restrict the point of view based on our program P1, then it means that this analysis result represents the possible behavior of this program P1. So this is the idea of meta-level static analysis using the definitional interpreter. So using this idea, we automatically derive static analyzer for JavaScript to support all the modern language features. So you can see that our derived analyzer can soundly analyze all the programs in a sound way, but the manually maintained research-oriented static analyzer failed to analyze most of the programs support having the new language features. But the problem is that if we derive these language tools from the scratch, it is really slow. The problem is performance. So I think it is not a good way. So we want to not directly not drive all entire language tools, but we want to update existing tools, not only static analyzer, but also other transpilers. It means that, for example, we want to update the Babel or SWs to support for each new language features, or if we want to support new language features in existing dynamic analyzers and so on. So this is ongoing work. We want to do that as the next step. So all these tools are integrated in our toolchain ESMeta. And if you're interested in, so please visit our repository. You can actually evaluate, execute all the features. So yeah, thanks for listening. And yeah, that's all. Thank you.
Yeah, thank you very much for testing that. So, yeah.
Yeah, thanks for this talk. This interactive debugger looked like super cool. So do you have any insight in like who's the audience, who people are using that actually in practice, and who are these people who are using that?
Audience evidence tool. So actually, I think there are three different users. So the editors, the maintainers, all the proposal writers, so who can contribute to the specification, and also the developers of the language tools. So I think they really helpful. They are really, it is really useful to give some more understanding of this different semantics for that for these three different users. I think that they are some possible audience of our interactive debugger, I think.
So even the specification writers themselves are using that, you're saying? That is, okay. They're debugging their own specification that way, or?
So I think it is, I said this debugger, but it is really helpful to just understand what happens, the edge cases of the semantics, not just debugging, just understand what happens, why this program produces this one, what is this edge case, what is the meaning of this edge cases. Yeah.
Okay, cool. Thanks.
Very boring question. Could you show the URL of the debugger again? I want to try it out.
Debugger? You mean this one? Yeah.
Is that publicly? Okay.
Yeah. So this is online. You can visit this online link. You can. Yeah. Also, there is a demonstration video, so you can see how to use it, and also in our ESMeta repository, you can visit. Then you can see the instruction video, and also. Yeah. Yeah, it is really good. Yeah, I think it is really good. Yeah, you can visit this site, and you can find all the instruction video.
One very dumb question on your one slide you had, where you had the example with the bug, like the
examples of
the two number, and then using comparison, or was it the round function, right?
That's the round. Yeah, the type analysis on the specification.
Is that just a type, or is it actually true that math round true is 0 and math round false is 1?
So,
green box.
Green box. Oh, you mean this is 1 and 0? You mean?
I would expect the
other I think I think it is a mistake. I think also, yeah, it is 1 and 0. Yeah, you're right. I'm sorry.
It's JavaScript, so you never.
You're right. Yeah, true must be 1, and yeah, first must be 0. You're genius. Exactly. I'll fix it.
Yeah, sure.
Okay. So at the end of your JSTAR section, you showed that there was like an assertion generator, and the assertions that you had on the slide were really simple, right? Like x strictly equals some number.
Yeah.
That's I'm sure just a simple example for the slide. But there are like many kinds of values that we can arrive at after running the program that you can't like test very simply for that. So like, what do you do for like complex objects or like functions, testing their like behavior? How do you do that?
So actually, I just showed the simple assertions, but for example, this is always supported in our association injection. So only this single really simple function definition, our association injection automatically generate the assertions for the prototype chain or property description, writable enumerable, and so on, and also the orders between the properties. So this because JavaScript, the property orders deterministically defined based on their creation time. So we support all these assertions to support the various kinds of properties.
Okay, so like most of the aspects that are observable about a property, but like a function is going too far, right? Like its behavior, trying to assert that. I don't even know what you do. But okay, yeah, thank you.
Okay.
It gets more complicated.
Okay, yeah.
Any more questions?
Thank you for the great talk. This is super impressive work. About like where you start from your IR that you derive from the JavaScript spec. I was wondering if you've considered having some front end for like other languages, basically. Like what if I want to define some other languages using your like meta language for the spec, then I could get all of these tools from that automatically. Just wondering if that's something you considered.
Yeah, so actually, someone write down some language specification for other languages using our IR. They can use our older tools. But actually, this our meta language specialized for JavaScript semantics. So I don't think it is a good way to use our meta language for other languages. I think they need to design their own meta language to import their own thinking and point of views. And so I think they have different insights for different languages, so they can use it. But I think it is better to define their own meta language to do the same things, I think.
Cool, thank you.
Yeah.
Any more questions?
So it seems like you're taking benefit of some of the kind of notation that has been introduced in the ECMAScript spec, like the question mark and bang, which is sort of like monadic operators, if you want, right, and the exception monad. So that was not there like 10 years ago in the ECMAScript spec, right? So that was gradually introduced. I think the language was more stylized, became more like a programming language. So I guess my question is like, how much do you depend on that? And would you be able to do that if they had not like more stylized forms like that in their prose?
So I just strictly follow the current style. So yeah, I think our goal is not that introduce new style or writing style. So we just strictly follow the current writing style to mechanize or making executable the current spec. So the goal is that way. Yeah.
Sure. Yeah. So I guess you, in a way, were lucky that it was already there, but you didn't also had to propose something new being added, so that the current state was in work quite well already.
Yeah.
Okay, cool.
Okay. You're right. Yeah. You're right.
Yeah, I remember that. Thanks.
Thank you.
Last question.
Yeah, thank you for the great talk. I'm wondering how often does the spec evolve such that your tools break and you have to like patch it to then work again? Because I can imagine they have the freedom to just like add whatever they want to the specification, but then it means that your tools need to adapt to their changes. How often does that happen, and how often is it a hurdle?
I don't know the exact number, but maybe once or twice per week, I think.
That'd be like break the integration. That's the question.
How often break? You mean the how often?
They have to update the tools to support new like phrasing and
Ah.
stuff. It's maybe like twice a year. It's really it's
yeah,
quite
exactly.
uncommon. But
You're right. Yeah.
the
I'm
the
sorry.
team is very quick at responding to those kinds of things quicker than it even needs to be, right? Because yeah, I'll get into it in my talk a little bit more, but we have ways of just like adding exceptions so that we can skip things that are new and unsupported.
Yeah. Thank you.
Yep, thank you very
Okay.
much.